this is the first of the spring 2021 lectures. So they'll be the first Thursday of each month, February, March, April, and May. And so we'll stay in touch with about next month's, but certainly I think two of the next three will be my State of the Bay seminar, and I believe we're also going to have the Shinnecock Bay Restoration Program giving a seminar as well. But for this evening, it's my distinct honor to be introducing Walter Klein as our seminar speaker. As it turns out, if I'm not mistaken, Walter, you're not just a New York native, but it looks like a Long Island native.
I can say Long Island with everybody. Yeah.
Okay.
Long Island. That's right.
There you go. So a Long Island native who went to Hamilton College, got a degree in geology. He did some work with the Navy. I'm going to ask him to give a short overview, but so he went to the Navy Test Pilot School and works for NASA now, flies planes, and and uses that to understand our Earth. And it was just today, actually, in my biological oceanography class, where I was explaining how when we used to have to rely on boats to understand the ocean, we learned a little bit. But when we started to rely on things like planes and satellites, we learned a heck of a lot more in a much more rapid fashion. And so I think we're all going to learn and understand the great power of being able to observe the Earth and our oceans from a great height. And it's a real honor to have Walter here. This presentation is being done in conjunction with the Montauk Observatory and their lecture series. So we've combined forces before for seminars, and it's fun to get a speaker like Walter here this evening by tapping into both SoMAS and the Montauk Observatory. So sit back and enjoy. And Walter, thank you for joining us, and I'll let you take the stage.
All right. Thanks, Christopher. I appreciate it. Well, hello, everybody from California. It's nice to see everybody. And yeah, I am a Long Island boy from West Hempstead, and had my entire childhood and my teens spent out there. It's very near and dear to my heart. But as would have it, I got into the Navy and never looked back. Continued on heading west from Florida all the way to Hawaii, where I wound up retiring. But I started my career in the Navy and flew strike fighters, the Grumman aircraft, a couple of them actually, one of the A6 and F-14, big out on Long Island, and also I wound up doing that for 27 great years, and then somehow got involved and got accepted to fly for NASA as a navigator and mission director operating the airborne science airplanes that we're going to talk about here. So, but before we go on, I just want to thank Courtney, who's going to be rolling the slides here. She's works at SUNY there and has been really, really extraordinarily helpful in getting this done. So thank you very much, Courtney, and hats off to you and your skills. So anyway, without further ado, what I like to do is go through about 20 slides with a lot of pictures, not too much writing on it, just kind of give you an idea visually of what we get to do and what your tax dollar actually pays for, and kind of go through each one, and maybe a sea story or two involved with those. And then afterwards, as I understand, within the full hour time, we'll have a question and answer time. So anyway, without further ado, Courtney, we'll start rolling. For the next slide, please. She has total control. There we go. All right, like I said, this is my first test flight in Shinnecock Bay. No, this was Tayana Bay, and props to the photographer who took this picture. I see her here, my mom, and this is where my love of the ocean and love of nature started from my times in the waters of Long Island. And anyway, that was my initial qual on the research vessel USS Wooden Boat. So next slide, please. Okay, so from little wooden boat in Tiana Bay to looking out the starboard side of the NASA DC-8, you can see a couple of the engine nacelles there. This is the primary platform that I get to fly in. It's a suborbital space station. And this particular shot, and most of that you'll see with the DC-8, are going to be taken over Antarctica. We fly and have repeatedly flown over like 11 years, sometimes 3 times a year, over the entire margin of ice margins all the way to the South Pole, using LIDARs, radars, all kinds of sensors, sponsored by all kinds of university consortia and other scientific organizations to look at the ice and the movement of the glaciers. And what's interesting of it is the aircraft is a airliner size, and can move at 0.82 Mach, but we're operating it in an area that you really wasn't planned. It really wasn't designed to go, and that's low level. Here we are about 1,000 feet above ice level, AGL, over a large ice sheet. I think it's the Getz ice sheet, and photos will never do this justice because it's so vast and so big. It really is. You got to get on a big computer with a big picture and high definition to really capture it, because you can see the curvature of the Earth on a good clear day from this level. It's quite astounding. So this was taken probably 2018. I've been there a bunch of times, like 37 times, I think, 37 sorties over the ice, and we are basically plowing the snow, so to speak, looking repeatedly over the ice. And I'll show some more of the great shots that we get. Next slide. There we go. Okay, so the NASA Armstrong Flight Research Center is where we're based out of. It's in the desert, in the Mojave Desert, where I am right now in California. And we get to fly a lot of different kinds of pointy airplanes that do a number of things. These are the primary airborne science ones. The upper left is a ER-2, which is a like the Air Force U-2 aircraft. We've converted it to look at the Earth at high altitude. And then the upper right's the DC-8. We're turning there. That's the lake bed where the shuttle used to land. You can see the runway behind it. So that's us doing a tight turn over the lake bed. And then the lower left is a Global Hawk, which is an unmanned big old thing that we've converted to fly over hurricanes and over remote areas. That can stay airborne for up to 36 hours, which makes it a very unique platform. And then the right is a G3 Gulfstream airplane with a pod on the bottom, and that little pod is leading to hopefully soon doing earthquake prediction, like figuring out that there's going to be an earthquake before it actually happens. So it's called a synthetic aperture radar, repeat pass interferometry, a lot of fancy words for the Jet Propulsion Lab created this thing, and is well on its way to doing earthquake predictions, which is awesome. Next slide. So a beautiful picture of an iceberg that's calved. You can see it up in the front there. This is on one of the missions a couple of years ago that we did, and the magnificent desolation, like Buzz Aldrin said, is just absolutely stunning. And the colors of blues and hues that you see flying over these things can't be understated. That particular one is a free floating iceberg with the ice behind it kind of backed up against it. That baby was free floating, and eventually we tracked it again a couple of months later when it detached. But just a really stunning photo. And these are the kind of things we get to look at from the DC-8 at low level. Next, please. There's the DC-8 again. It's this is the original airline body that came out in 1953, I think it was. And we re-engined it and pimped it out, and it's a one of a kind. There is no airplane like it in the world. We can carry 45,000 pounds of gear, and up to 12-hour flights and get up to almost 38, 40,000 feet with it. Go everywhere in the world with it. We've done. I'm talking mostly about ice, and then later I'll talk about the other aircraft that does the studies from the heavens. But this aircraft does everything from studying coral reef bleaching to pollution studies from pole to pole. And we take it and base it out of other countries. In the case of going down to Antarctica, we go to Ushuaia, Argentina, and Punta Arenas, Chile, and base out of there. And basically, it becomes a home away from home. We'll stay deployed for up to 3 months, usually 2 months is tops. But interestingly enough, since we're NASA, when you show up with a bird like this, we're not doing any spying. We're not doing anything, but it's open for public use for science. We always are really well welcomed, and it's just an honor to fly in an airplane like this. Its design it's one of the rare aircraft that has a undetermined amount of life left in it because of it's over designed. So one of a kind DC-8 NASA 817. Okay, next slide. Okay, so if hopefully your screens are clear enough for this. There's a this is an example of the flights and sorties that we did. So they all lead off the left side there from Punta Arenas or Ushuaia. And every day we'll fly 10 to 12 hours. We rotate crews, and they're long sorties. It's 3-hour transit at least, and we'll fly all different types of ice structures. There are, I think the Eskimos have 30 different types of words for ice and frozen water, and we've seen them all. Whether we're flying over the glaciers that are feeding off of the plateau, or off of that arm that sticks off. You can see it. That's the Antarctic Peninsula, which is absolutely enormous. It's like 5 times the size of the Sierra Nevada mountain range. Interestingly enough, and you'll see in some other photos, there's a lot more dirt sticking out in mountains than you think over Antarctica, and we'll show you some of those pictures. But it does go from sea level all the way up to 10,000 foot above sea level. That's the South Pole, 10,000 AGL, and these are the sorties that we flew in 2018. So, next slide. Next slide. Another beautiful photo of sea ice rafting. This was taken a little higher up I can't remember why we did that. We were doing some special returns on that ice. It's just as gorgeous flows are bumping into together and stacking on top of each other. And although it looks like glass, each one of those flows is probably about 3 or 4 feet thick. And you start seeing things that you never thought you'd imagine that existed. And each, almost all the flights that we did, there was always some type of a phenomena that you see as you're flying over the ice. We typically would do these flights at the end of the winter in the southern hemisphere, because that's when it's been coldest, and that's when the margins of the ice are on the furthest around the continent. But yeah, just a beautiful shot of flows drifting. Next. And of course, the South Pole looks kind of desolate, because it is. We fly over them at altitude. We're not allowed to fly below 10,000 feet because they got all kinds of instrumentation and things that they're studying there, and even the sounds of an aircraft would interfere with those instruments. But we called them up on the radio, and they were wintered down, which meant there's fewer missions going back and forth to support. So give them a little eye candy and fly over on top with a contrail. So we got this picture from our DMS camera. But it's an internationally run facility, and that's what it looks like from 10,000 AGL. I hear the food's good. Haven't been there yet. So next. Okay, that's a gorgeous shot of coming onto the margin of an ice sheet. That, just to give you a perspective, because it's really hard, even when you're flying and you do it all the time, we still don't have the eye perspective. Those sea cliffs are like 200 feet high, and that margin was as far as the eye could see to the left and to the right of the aircraft as we were coming onto this plateau, if you will. So it's, part of it is floating on the saltwater ocean. This is freshwater ice coming. Eventually it's going to calve off and become a giant platform iceberg. But the magnitude just can't be understated, to see these things. And then you can't see it in the photo here, but there's usually 10 to 12 times the amount of blue color underneath, because that's the displacement of the water, is such. The ice is, most of it is underwater, as you probably know. But just another beautiful shot of what's probably going to calf off as it warms up. So anyway, next please. Okay, that's a shot of the Larsen Ice Shelf, and that was in the news about 3 years ago, where we happened to be flying by that area, and we noticed a fissure as far as the eye could see, and that's the fissure. It's about 180 feet deep, and that is not the moment of, but close enough for where the size of Manhattan part of the ice sheet was separating. And so to be able to, bear witness to it and to measure it, and we came back the next couple of days and looked at it, and it made the news because it was, it was a pretty big chunk of ice as it was moving off. But it does happen. I mean, it happens naturally. It's supposed to happen, and in what frequency, that's a whole nother debate. But we had the instrumentation to fly down that crevasse, and it gives the rate of motion and the displacement of the ice as it's left it's the mother of the ice shelf, the Larsen Ice Shelf, and it actually pops up a little bit because it's floating on its own as opposed to floating on the tongue. And so we have the ability to take the airplane and fly down that, not in it because that's too close, but have a really good vantage with multiple cameras and all that for viewing an event which doesn't happen all that often. And eventually it was captured by the satellites that we have. So next. That's a beautiful shot of the top of a glacier that's been moving, obviously, and filling up again with ice. And what's really interesting about it is this was taken from our DMS camera, which is a downward-looking camera that you really have to have a have a good timestamp on that, because these things can be analyzed and overlain with our other instrumentation. We have a magnetometer, which basically measures magnetic, mass, just to giving us thickness and finding the base of the base of this ice, to different types of ice penetrating radars. But that's a shot of looking straight down. Next. Okay, so now we're going to pointy airplanes. This is one of the, I put that in there because it's one of the Navy aircraft that we've converted and put into a NASA, NASA colors. We use these for proficiency, but we also use them as test articles or flying test articles. So like, for instance, this particular aircraft, we had the nose, replaced the radar that the Navy has, a weapons radar, and replaced it with was a prototype for the Mars lander. So before we did our first landings with that vehicle, we tested it in this airplane and basically went into dive patterns, very steep dive patterns, to test high rate of grounds and accelerations and decelerations. So, yeah, I thought I'd put that in there because pointy aircraft that land on ships are always fun to look at. So Next. And that's the Gulf Stream, the Uavsar that I was talking to you about earlier. Converted aircraft that was once part of the Air Force. And interestingly enough, NASA takes a lot of aircraft that were flown by the military, some privately, and take them and convert them. Not often do we buy or get new aircraft. We get them, strip them out, and reinstall racks for instrumentation and other strange things, because Gulf Streams are not designed for this kind of stuff. They're designed to be sleek and fast and get somebody from A to B and not spill your coffee. But here we installed a rack system on the bottom, and you can see that pod that the Jet Propulsion Lab created. And again, as I alluded to earlier, that's going to be used to study earthquakes and movements of the Earth, and hopefully lead to earthquake predictions. So I get to fly on that too, which is a lot of fun. Next. Okay, so now we're going to shift gears from looking down and looking at ice and Earth to looking up, up to the heavens and looking at things at night. This is the NASA SOFIA aircraft. It's a 747, and you can see that we cut a big hole in it, big square hole, to put a telescope, a 2.5 meter mirror, which sits in a cavity in the back, and people and scientists operate it forward of that. There's a whole, and I don't have, I've got a diagram of that. We'll fly up to 25 persons on board, and then of course the flight crew were up front and take the aircraft where it needs to go. It's an elegant solution for a problem that all telescopes have, besides putting them into space, which solves not having interference from atmosphere. We get up to about 42,000 feet with this aircraft pretty quickly, and we'll go for 10 hours and do long transects at night only. It's an infrared telescope, and view all kinds of phenomena that I'll talk about a little later. But it's always at night, and it's in the infrared spectra. So it's not like Hubble, which is optical. This has other utilities, and the system is a highly gyrostabilized side-mounted scope, and it's with a partnership with the German Space Agency. And the Germans are exceptional with their optics and their abilities to grind glass and things that are just, they're real expert at it. And we have a consortium of German scientists and crew that operate the payload, and then it's on a NASA platform, and it's permanently mounted. There are none others like it, and right now it's currently in Germany getting some upgrades to the airframe and some inspections. But we're going to be flying out of Europe to look at the heavens. Typically, we fly it out of Palmdale, California. Here, we'll take off and fly over the ocean or over the continent, whatever the scientists want to look at, and then land back here. So you get a full 10 hours, 4,000 miles, and always land where you took off. And that's our cycle of work with them. And then when summer comes here in the Northern Hemisphere, we take the aircraft and go to New Zealand out of Christchurch. And since it's winter down there, we need the winter sky. It's preferred winter skies. They're clearer, and there's a number of other scientific reasons. And we share the hangar with the Antarctica aircraft that normally would go from Christchurch down. It's empty, and then we fill in and operate out of there, looking at the southern sky from the Earth. So it's a beautiful aircraft. It's a wonderful ride, and a really great thing about it is that you can. There's a program that we take educators on board, and they'll go through a month's worth of training and and from safety training, egress training, to learning how the system actually works and how the missions are planned. And then they'll fly for 2 or 3 sorties. So if you know any teachers out there, and it doesn't matter, you could be math, you could go for art. It really is, it doesn't matter. It's got to be an educator. It's a wonderful outreach, and we're going to start flying that again soon. Hopefully sooner than later, after all the lockdowns come off. So next, please. So some of the areas of interest that we look at, and I hope, well, if there are any astronomers there here, please excuse me as I batter all this kind of stuff. I'm not an astronomer. I'm a geologist and a flight officer. So, but I do know how to use some of these big words, and I get to listen to them brief their areas of expertise, because every night there may be 3 or 4 different types of scientists looking at 3 or 4 different types of things on the same mission. So, galaxies and galaxy origin and center, the interstellar medium of the Milky Way, what is it made out of? The formation of stars and planets, and planetary science. I mean, those are, very broad areas that cover a lot, and we'll have scientists who fly on board with us. And of the most recent note that this aircraft made the news was that we found the evidence of water, ice water, on the moon. So as we go to the Artemis program, which is going to, the next person's on the moon, hopefully soon, the looking for water is going to be a very big part of it, at least crystalline water, and we're going to be looking at it with the aircraft this year. So exciting stuff, but it's a broad variance of things that we look at with the telescope. Next. So there's the inside, a schematic, like I mentioned earlier. We sit upstairs, flight crew of 3 to 4, depends how long the missions are. We have flight engineer, 2 pilots, navigator, and then down in the basement, as we call it, we got all the scientists, and they've got different positions, whether they're in the mission control, or they're working on the actual function of the telescope, or operating the aiming of the telescope. It's a really big team effort. It takes at least 14 people to get a sortie up and out each mission, and you're really busy. The least busy guys are us in the flight. If we've done everything right, you put it on autopilot, and it flies these long transect lines that we have to be spot on with time. We plan plus or minus 1 minute for every waypoint that we go to. So if you could imagine, you're flying to Hawaii, and you've got waypoints every 100 miles. Each of those waypoints we have to be on that waypoint plus or minus 1 second. So it's a timing solution, because of course the airplane's moving, the Earth is moving, and the telescope is moving for turbulence. So it's being aimed very specifically, and that our whole team works on getting that done. So the below part picture's got a good shot of the scope, and you can see there's a bulkhead. A lot of people ask, well, does it get cold in there, and how does it work? But we're completely separated from the telescope. It's floating on a thin layer of oil, and I'll show you a picture of that. So there's basically a cabin environment forward of that bulkhead, and we steer the telescope once we get the doors open. And then the back is some more environmental control systems. It's got to be kept at a very stable. You want to limit all your variables, right? So you want to limit, your time, distance, heading, vibration, radiation, you name it. So a lot of that stuff is controlled by a lot of people in the cabin, and plus automatically in the ECS back of the aircraft. So next. And there she is, looking from the front. So if you're sitting in the back of the aircraft and you're the mission director, you get to look at this. So it's extraordinarily heavy and counterweighted because of that. But that entire system, you see the blue ring where it meets the silver in the furthest back on the bulkhead, that's floating on some highly specialized, pressurized, temperature-controlled oil to make it stable. And it's really quite interesting to fly and look at it when you're flying. So if you turn around when you're airborne and you're in a little bit of turbulence, you're feeling the turbulence in your body and the aircraft is moving, but that thing is rock stable, gyro stabilized. So you look at it and it's not moving and you're moving. You could actually get yourself sick by looking at it. It's quite an amazing phenomena, but it's a fantastic instrument, and it has a lot of applications as you saw earlier, and different universities vie for, sometimes 2 or 3 days to fly in the vehicle, and it's always pointing at something different on each leg, which is pretty amazing. And I put in there it's I can't see what it says up there, but it's a large infrared telescope. It's a Cassegrain reflector using a primary mirror and remotely configurable hyperbolic secondary. If anybody can explain that to me in less than one sentence, I'd really appreciate it. Suffice to say, the Germans made it, and it's a fantastic piece of gear, and it's got a lot of years ahead of use. So next. And that's a view taken from a crane outside when we were on the deck, looking at the mirror with both doors open. We don't like to do that often on the ground because it's glass. And if any of you guys have telescopes and understand anything with that, you want it as clean as possible. So a micro speck of silica that drifted down on it will be picked up by the sensors. So it's a hyper super clean environment. But when we open it up at altitude, you can see the fairings on how it's fared on either side. The boundary layer or movement of air across the airframe moves up on that fairing and goes over the cavity. So there's no buffeting or air movement in that cavity while you're moving at 600 miles an hour at 43,000 feet. It's a pretty amazing aerodynamic system that we developed. And yeah, it just opens it. We call it the garage door. Open the garage, close the garage. Trivialize it, but it really is. You can barely feel it moving as the doors are opening and closing. So, shot of the scope. Next. Okay. Well, I just want to finish up with this. I'm a navigator, and this is the Polynesian navigator star chart that I have on all my desk savers. So I just wanted to finish up with that, and I guess as we transition into the next questions and answer time, we can start doing that, and really any questions that you might have, whether it's NASA as a whole or airborne science or the telescope, we've got about 40 minutes to do that. So with that, I'll leave it to Courtney to start it going. Christopher, sorry.
I'll just jump back in, Walter. That was an incredible talk, so thank you. Really amazing stuff. And actually, a personal. My dad worked at Grumman, so and used to do work out in Calverton testing planes. So you might have maybe even overlapped at some point.
Yeah, absolutely.
And one other thing I'll just say, just for the audience, again, we have a nice combo crowd here, folks both from the Montauk Observatory and from SoMAS. So if anybody from the Montauk Observatory is interested in seeing future marine science lectures, they're welcome to put their name and email in the chat. But for now, I think what we'll do is if people have questions, they can also put those in the chat. And Walter, I actually did have a question. I was hoping I could maybe kick things off as we wait for people to chime in. So for the work that you've done in Antarctica, looking at the ice, clearly you're getting a sense of where it's all breaking off and such. And I'm always actually really interested in Antarctica because I know that, of course, while the Arctic, of course, has been melting away at this super rapid pace, We all know about that. Antarctica, sort of, the ice, it's not been as dramatic. And I know it's been maybe a little bit more complex in assessing the change. So I'm just wondering, from your flights, do the scientists you're working with, are they uh, making measurements of ice loss or total ice coverage or ice volume as well? And if so, how do you have a sense of how the planes help facilitate that?
Yeah. So the guys that operate the instruments, they vary from Goddard Space Flight Center to University of Kansas on the suite of instruments. And ultimately, what we see afterwards, that once the scientists crunch the data, is like actual flowing of the ice, all the ice, whether it's at the pole and the plateau ice, or if it's margin ice, or if it's glaciers running from the steep terrain in the peninsula. The dramatic view of it is it's a different kind of drama, because as you know, it's a continent, right? So it's not being affected underneath, at least in the center portion of it is, as the Arctic is, right? Because that's all, there's no land up there. So the instruments, I mentioned the gravimeter. Actually, they're out of Lamont Doherty in Columbia. We call it Einstein's brain. That's one of the instruments. It's just it measures it does measures of mass, and it's an instrument that has been used repeatedly on different aircraft in our aircraft to get a change or a delta. So when we fly repeatedly, we are looking at literally over the same lines over the geographic part of the Earth to see where the ice has moved or how it shifted. And the presentations that I've seen are showing dramatic motions of movement. So the flow characteristics of ice changing based on this is your neck of the woods, so excuse me if I kind of sound like I'm making it up, but having a real sense of speed and acceleration of the movement of the ice off of the plateau, from the ice shelves down to the different glaciers. So in my personal visual experience of it, when we've flown repeatedly over the Shackleton range or a couple of the others, I've got handheld pictures of the change. Here's some ice, and here's a little less, and here's a little less, and now there's not as much. So empirically, I'm certainly not making a judgment, but it's dissipating, right? But there's certain areas where it's growing, right? Why is it growing? Well, it's growing because it's going so fast. The ice margin, it's like squeezing Play-Doh, right? It's kind of, or not Play-Doh, or silly putty. It squeezes out. So it's getting bigger, right? Oh, look at the margin of the ice is larger this year or for this decade, but it's collectively thinner. So we do the X, Y, and Z measurements really well. Um, I think through all the, gosh, it's been 12 years. And I mentioned the DC-8, but we have a P3 that does the similar types of things, doesn't have the same legs. But so there's a lot of data from our airplanes that show the changes and the deltas. And it's with lidars, gravimeters, and different types of radars. We have snow penetrating radars, reflectivity radars, and of course we try to do this if satellites are functioning. There were a lot of times where the satellites were not functioning. There was actually a hole from non-coverage, and we were building the sensor for IceSat, which is up now. When this previous satellite was up, and then now IceSat, we underfly the satellite. So I get my flight software to look at when it's going to be, and we do a timing control, problem, and we want to be over a certain point as the satellite's flying over. So we calibrate the satellite, and then of course when we're not there, the satellite's going over and over again. So yeah, it's I think the aircraft measurements using the same instruments or similar instruments that are on the satellite, plus we have in situ stuff, right? In atmospheric science, that's big, right? You got you're actually, we have some in situ measurement as well. Altogether, it correlates for a story of, you know, there is dissipation. So that's, yeah, no doubt.
Yeah. Yeah, fascinating. And someday I need to come up with an instrument that I call Einstein's brain. I love that.
Yeah.
Let's get some other questions. Again, if you have a question, you can type it in the chat. I'm gonna and I'll read them out. So we have a question here. This is from Julia, and her question is: are magnetic fields over Antarctica different, and how is the equipment you used affected by it or utilized towards some end?
So well, yeah, the magnetic fields on both poles are, all the lines of longitude, come to meet, right? At zero, everywhere is north. So the magnetic anomalies that are occurring below the ice because of the thickness of the mass of the ice plus the thickness and mass of the rock below it will change and alter the magnetic. We can detect it with the gravimeter, it's called. And of course, then there's the atmospheric electromagnetic interference, if you will, which causes aurora borealis, or Australia borealis, right? Yeah, or aurora australis. So those things are always, there's a lot of movement of the Earth's magnetic field in the atmosphere. When we're flying there, we got to be very aware of that for navigation, because there's no 911 there. You get lost. It's, you become a legend of. So to answer the question, yes, there is a great variance, and it does occur on both poles, but it's different because of the effects of the rock and in the Antarctic.
Okay. Question from Charlotte, and she asked, do you fly SOFIA any differently than you would a normal 747?
Yeah, a little bit. So you want to be really smooth and easy with maneuvering the aircraft, especially when the doors open and you're observing. So we kind of fly it, we kind of handle it with kid gloves because you want as little vibration as possible, as few as inputs as possible. So that said, yeah, we fly it like we don't want any coffee spilled in first class, but when we have to, you close the door and we, say horse it around, but airplanes can do a lot more than what you're subjected to in an airliner. And occasionally we have to do that for tests, for functional check flights. But operationally, we want to get up as high as possible, as quickly as possible, in clean, clear air. So we fly like an airliner in that respect.
Okay. All right. Again, if you have questions, please type them into the chat. We have a question from Amanda, and she asked, do you collaborate with other teams or organizations outside of NASA in the process of this research? She also says thanks for the talk.
Oh, yeah, you're welcome. So, yeah, we do a lot of, we're really good at that. The world of airplanes allows us to have more access for scientists and students to be part of the process. But every mission is a really big collaboration, and they vary. Some of the atmospheric chemistry missions might have, with the DC-8, we'll have 27 instruments, and then so you have 27 teams, and they rotate through, and technicians, engineers, and all that. So you'll have hundreds and hundreds of people in the field, because we also set up labs as well. Once we're, whether it's here at Palmdale or out in, deployed. And it becomes a real logistic process for getting everybody together, from, badging to hotels, to access to the airplanes, on the aircraft. So we're really good at that. I would argue, compared to other government organizations, we're probably the best one, because we, these are we call them customers. I don't like to use that because it implies like you're going to a 7-Eleven, but someone's paying for this. And if you could have access and show them, what your instrument's doing on the airplane, we highly encourage it. And as I mentioned earlier, there are programs that are for the public, like the Astronomy Ambassador Program I mentioned for SOFIA, for any teacher of any kind of grade or any level, and also a student airborne research program, which allows undergraduate students from around the world to come on board the DC-8 and fly with us. So those are good things. When you Google, if you want to afterwards, Google NASA Airborne Science, and you'll come across all these things. So lots of outreaches.
Okay. I guess people have been staring at the chart that's up, and we did have the question. Can you explain the chart on the screen? Thanks.
Explain the chart on the screen. Okay, I knew you would do that. Okay, so I've spent, my wife and family and I, 20 years in Hawaii. So all of my daughters are born and raised there, and we've got a lot of influence from Polynesia. And I've got some dear friends that are native Hawaiian, and I realized after living there that the beauty of their and abilities to excuse me for 1 second, would you please? We have a very talkative cat, and my dear wife is removing him right now because he had a lot to say. So yeah, this is great about teams and all this, right? You get to be in everybody's house. So yeah, I kind of embrace this chart because of the abilities of the Polynesians to navigate without any electronics, without timepieces or anything else in the Western way. And I've been trying to study it. And this particular chart you're looking at is a star chart, and it depicts the four quadrants: north, south, east, west, and the stars that represent those sections in the quadrant for navigation purposes. And it's actually it is complex. So, the North Star, the word for north is Akau, and then Hokuapoa'a, which is the North Star, or Polaris is what we call it, is on the top. So I like to keep this out because I figure once I retire again, I'd like to be able to navigate using their system, not GPSs and other stuff. So that's why I put that on there. Remind me that you can do it. You don't need electricity to navigate.
And I think it looks like there's also a question about, maybe it's just elaborating on what navigating in the Southern Hemisphere is like, or chart navigation for the Southern Hemisphere. I guess this is for the more towards the northern, but I don't know if
Yeah. Chart navigation.
It says, how would you use this in the Southern Hemisphere?
Oh, how would I use this one in the Southern Hemisphere?
Yeah.
You know something? I will say, I'll be humble. I don't know, because I've not learned to sail in this or look at the charts for the Southern Hemisphere. This was designed for Hawaii, which is in the Northern Hemisphere. But there is another type of star chart that they have that I don't know what it's called. So I'm going to learn that. I'll get back to you on that one.
All right. Well, if there's any additional questions, you could punch them in. I was just going to ask you, Walter, what's your favorite of the planes to fly at this point?
Well, okay, I like flying. I got to separate it. So we got Navy and then NASA. Navy airplanes was landing anything that lands on a ship. That's a lot of fun. So I got a chance to do that. In terms of my world with NASA now, which I've been flying all these airplanes for a while, I like the DC-8. I mean, I love all of them. Don't get me wrong. It's like saying, what's your favorite child? The DC-8 is just it's got a different, it's variable. You'll have different scientists from different, whether they're a biologist or an astrophysicist or a geologist. We fly all of those. Whereas when you're doing the SOFIA missions, you're astronomy, and you might have different types of astronomy being looked at, and I know there's many subsets. So so flying at night, looking at the heavens with SOFIA is gorgeous. It's a calm environment. The planning for it's not, but once you get going, when things are working, it works well. The DC-8 will fly at low level, and there's no margin for errors doing anything in an airplane low level. So that makes it the dynamic. I'm usually a little more tired after flying those missions because of it's more dynamic and the ground is closer to you. So, but they're all good kids. I love them all.
Love them all equal. There's a question that Patricia is asking, what's your next mission?
So the next mission I'm planning on is ER2 mission, which was that high flyer that's going to be studying some environmental characteristics over the West Coast. So I'll be doing plans for that. And then that lasts for about 3 weeks. And then the 747, SOFIA comes back, and I'm going to get because a lot of us have lost our qualifications because of what's been going on in the world. So I'm going to get just requalified, re-educated, and fly the SOFIA aircraft as the navigator and as the mission director this summer. And I think the most of what I'm hearing is that we're going to be looking at the moon a lot. So that's the next mission. And then the DC-8, we're going to go to either Puerto Rico or the Virgin Islands to study hurricane and foul weather genesis. So there's always something. Do a lot of traveling here.
Sounds pretty exciting. I bet you're eager to get back to it.
Oh yeah, absolutely. Yeah. Being on the road is a lot of fun. And now, since all of our kids are done with college, my wife can actually come with us, and we can actually have a vacay afterwards at the locations. So
there you go.
Yeah.
Okay. Well, there's someone asking if you've been to Antarctica, but certainly you've been there by plane and.
By plane, never been on it. I'd like to. That's another bucket list when we get to stay down or stay any of these places. You meet some really great people, and we got a chance to fly a Chilean explorer who had just come back from cross-country skiing to and back from the South Pole.
Wow!
Right, he took some national. Yeah, he's that guy with the beard. He's one of those guys. If you want to be stuck in the ice, it's with him. Anyway, I have an open invite to go back down to Punta Arenas and do some trekking. That's hiking with a real pro in the glaciers. So that's my goal. I'd like to go to Tierra del Fuego, which is the southernmost part of the South American continent, and do some hiking and stuff there. And then the North Pole gig. I've done a lot of flying over we have done a lot of flying over the Arctic. And that would be maybe a trip to Greenland would be a next, but never been boots on ice on any of those places.
Okay. Well, maybe safer that way. I don't know.
Yeah. I don't know. It depends. You get a false sense of security when you're drinking your hot cup of coffee, 1,100 feet over the ice, 3,000 miles from nobody.
Yeah, fair point. I just recently reread Endurance Shackleton's story. So
what a great story, right?
Yeah.
Actually, interestingly, the guy that I mentioned, Jose Contreras Stading is his name. That's the explorer from Chile. He is enamored with the Shackleton universe and has actually gone to those places and skied and simulated on a small boat going to Elephant Island. Yeah, I couldn't imagine that. A year and a half on the ice.
Yeah.
Right.
Amazing stuff.
Yeah.
All right.
Yeah, we get trained to survive, but it's a no-go. If you land there, you stay in there.
Yeah, exactly. Well, Walter's been totally fascinating, and I missed in my intro. I didn't say 28 years in the Navy, so thank you for your service to the country as well. And
thank you.
And thank you for this talk. Really fascinating. And I'll have to talk to Brian Coley at SoMAS about your collaborative projects as well.
Yeah, absolutely. Look forward to it.
Yeah, but thank you so much for making the time. And we've recorded this, so we'll put it up for people to look at again. In fact, I can guarantee you the first person I'm going to tell is my dad. He's going to be thrilled to see this one.
Right on.
having retired from Grumman. But anyway, thank you again, Walter. It's been a real pleasure. And
Thank you.
yeah, I wish you the best and hope you get up in the air flying again soon.
Absolutely. Hopefully we'll meet in real time, real faces sometime. So
Yeah,
it's nice
that
to
would be
talk to
great.
everybody, and we'll see you all at the observatory sometime. How's that?
Sounds good. Thanks, Walter.
You take care. Have a good night. Aloha, everybody.